Okay, so we've had a look at sample variability, and we should now understand what sample variability is by looking at the videos and so on. We know that when we take a sample of a population, we get a snapshot of what's going on in the population, but every time we take a sample, they're going to be a little different from each other, and they're going to be different from the population, and that's called either sampling error or sample variability, and we cannot eliminate that. So however, every time we take a sample, it's going to be a bit different from every other sample. Every time we take a sample of the population, we get only an idea what's going on. It's an estimate, but it can often be wrong. For this reason, it doesn't make sense to use a point estimate, a single value estimate, to say, well, this is what's going on in the population. It's better that we use some sort of confidence interval, some sort of interval, a range of values, like we talked about with time series. Now, the other aspect of sample variability is the size of the sample. The size of the sample is very important. And I'm just going to show you this GIF. This GIF here is a sample of 10. So this is like doing thousands of sampling of 10 from a population. And you can see that the box plot, and I know it goes very fast, but you can see the blue is basically the medians, right? From the various samples. The box plots are shifting in various positions, and the medians are changing a lot. And there's a big shift and a big change when you're doing samples of 10. So there's a lot of sample variability in a small sample. Now we do a sample of 100, which is a pretty good size, and you can see that the variation where the boxes shift and the blue is in a much more narrow position, right? It's much less variation. There's still variability, there's still shifts and changes, but it's a lot less. There's a lot less variability, a lot less shifting of the boxes, and a lot less shifting of the medians, for example, which is that dark line that's coming down. And then if you take a sample size of 1,000, you can see that there's next to no shifting. That the samples that you're taking that are size 1,000 are very, very similar to the population parameters. Like the median varies a little bit, but not very much. It's pretty much falling very close to the median of the population, and the boxes are pretty much the same. So you're getting a much better view or inference from a large sample back to what's going on in the population, because there's a lot less variability. So if you look all the way up here, we can get all kinds of different things that aren't going to samples with medians and box plots that aren't going to look anything like the population. It gets a little bit less when you look at 100, and then by the time you get a sample size of 1,000, you can see that the shifts is very, very small, and we're getting a box plot that resembles very much what's going on in the population. So size matters. So although we cannot eliminate sample variability, we can reduce it by taking a big sample. The bigger the sample, the less the variability in samples, which means we have a smaller confidence interval, smaller range of values, right? So this confidence interval here is much, much smaller than this one, which is again much, much smaller than this one. So that's our range. Like that's pretty much our confidence interval there. And each time we do it, we get a much shorter situation where the confidence interval is much smaller. And so that the more narrow your confidence interval, the more confident you are that the sample statistics and the sample itself will reflect what's going on back in the population. Okay? Here's just another GIF, very similar. This is the population. This is the histogram of the population and the box plot of the population and where the median falls for the height of girls of age 12. Now, we don't get to see this. This is sort of what we call the unseen world, because we're not measuring the whole population. So we do samples. And here we've done a sample. We're doing a bunch of samples of 20. And you can see how much variability based on what's going on in the population there is. Sample size of 100, there's less back and forth, less shifting, less movement in the box plots and so on. There's still a fair bit, but a lot less. And then by the time we do 500, a sample of 500, we're getting a histogram that resembles very much what's going back in the population. The box plot has some variation, but not nearly as much. So that just confirms that whole idea that sample size matters, and the bigger the sample, the less variability there is. You can't eliminate it, but you can reduce it so you get a better sense from your sample of what's going on back in the population.